Amplifier, distortion, and feedback. That's what we're going to be talking about in today's video. Hey folks, I'm Gene Delasella with Audioholics. We got Jonathan see you again from Benchmark Media Systems. How you doing, John?
Very good, Gene.
It's always good to have you on the channel, talk some knowledge about amplifiers or just debunk myths. I think we're both on the same page about a lot of this stuff. And amplifier feedback is a complex topic, right? Because you have to know control systems. You have to have a deep understanding in math and theory and amplifier design. And many people misunderstand or misapply feedback. And you guys have a very unique way of doing feedback in your proprietary THX amplifier topology. And I thought it'd be a good idea to talk about this in today's live stream. So you could give us some illustrations, maybe give us some analogies that people can grasp. So it's not just all math. I think that'd be very useful to consumers.
Yeah, and in fact, we do two things, Gene. We don't just use feedback, but we actually use what's called feed-forward correction, which is not a feedback system at all. So it complements the feedback system. And what I want to do is give you an illustration that will help you understand what feed-forward error correction is. We're all familiar with thermostat in the house. We set the thermostat at a certain temperature, and the temperature ramps up, and it overshoots a little bit, and it comes down a little bit, and eventually settles out. And depending on the location of the thermostat, depending on the location of the heat vent, the heat coming in from the sunshine, all of these things can influence that feedback system. Sometimes they work very well, sometimes not so well. So to illustrate what a feed forward and feedback system are, first of all, let's imagine we've got a firefighter, and they're having a contest as part of their training, but he's got a fire hose, and there's a bucket over here, and the goal is to shoot water into the bucket, and the first team that fills up their bucket wins the contest. So he's watching where the water is going, and he's got a feedback system going. When the water is too far to the left, he goes to the right. If it's too far to the right, he aims to the left. He has to aim up and down. But the better he is at it, the faster he's going to fill up the bucket. But there's a time delay between the water going in the bucket and his actions with the hose. The wind comes up. Now he's got to correct for the wind. Let's imagine that now he's got an assistant, and his assistant's standing over here, and he's got his fire hat also. I'm going to put the badge on the front. I didn't give him his badge. There we go. So now his assistant can see where the water is coming, and he can move that bucket to get it underneath the stream of water. And now they're able to fill the bucket much more quickly, and they're spilling a lot less water. That spilled water is distortion in sense of an amplifier. What he's able to do is he's able to make corrections very fast. This guy here is not able to make the corrections as fast because of the time delay of the water going the 30, 40 feet or whatever he's shooting the water. And so this is feed forward. And this guy is just using feedback. Okay. Now, the question is, what does that look like in an electronic system? I've got a big amplifier, say it's a 100-watt amplifier or something. It's got a feedback loop. I've got an input signal, and we're comparing the output of the amplifier to the desired input to try to clean up this output. Okay.
Mm-hmm.
Now, we might have a little bit of distortion, say zero crossing distortion. We can have other contributing factors contributing to the distortion. If we were to amplify that distortion signal, it might look like that. If we had crossover distortion, there'd be other shapes in here depending on what kind of harmonic content we have. But we have that error signal. That's the distortion that we'd like to get rid of. There's a limit to how much of that we can take out with pure feedback, because it gets especially difficult when we have these high frequency components. But
yeah, because your feedback effectiveness goes down with raising frequency.
With frequency, and that's why if you look at a THD or THD plus N, it doesn't really matter, versus frequency, for virtually any power amplifier, you'll see that the THD increases as we go up in frequency. And so that might be 20K there, but we have this increase in frequency. That's largely because we don't have as much feedback available to correct the distortion at high frequencies. All right, now if you look at that same plot for an AHB2, it looks more like that. And it's because from this point on, we're primarily using feed-forward correction. Mm-hmm. And in this area here, we're primarily using feedback correction. And the two overlap, and it's a general crossover between one and the other. But the feed-forward error correction can operate as fast as this guy can move, versus the feedback can only operate as fast as, well, we're limited by this time delay. The time delay of the water going from the hose to the bucket, or in the case of an amplifier, the propagation delay through the amplifier. How long does it take the signal to get through this main amplifier? Turns out it can be slow enough that we have a very hard time doing as much correction at high frequencies. We can still do some correction at high frequencies, but not as much as we'd like to. We can do a lot more down here at low frequencies, but we have this rising THD versus frequency. With the feed-forward error correction, we don't have that. So what does this look like in the circuit? So we've got this output that's got a distortion component to it. If we take that output and run it into a little amplifier, I mean, it doesn't have to be a little amplifier, but if this was a 100-watt amplifier, I might only need a watt down here, okay? So I've got this signal here that's the desired signal plus the distortion, and I compare that to the clean signal, and what I get out here is just the distortion signal, but it's actually, in this case, inverted. It's that flipped over. Mm-hmm. So
would you consider this like a servo control?
No, nope.
It's not a servo.
It's not a servo control. This is a servo control. Okay.
Right. Okay.
The feedback system is definitely a servo control. This signal and this signal get passively summed together to go to the loudspeaker.
Right.
So we have distortion plus the desired signal, inverted distortion. The inverted distortion is summed with the distorted signal, and what we end up with is a clean signal here. And that's a rather distorted sine wave just because of the way I drew it. But
so is the output differential, or is it still single-ended?
It's single-ended. We wouldn't need this combining network. We wouldn't need this network if we were to invert the polarity of that and, you know, feed the minus pin and the plus pin of the speaker.
Right.
But if you did that, you wouldn't be able to use the amplifier in bridge mono.
Right.
And you'd get into other problems with biamping, you know,
The
because
impedance would be too low.
a lot of speakers, you know, they've got these bus bars on the back, and when you disconnect the various drivers, you'll find that lots of times the grounded side of the speaker is still connected across all of the drivers. Not always the case, but sometimes it is. And so if we were to do this, differentially drive the speaker with a correction on one pin and the main signal on the plus pin, you could get into trouble with certain biamping situations.
Wow, I've never seen that with a speaker unless it's biwireable but not biampable. Some speakers are only biwireable. Maybe that's what you're talking about.
Right, exactly.
Okay.
Yeah.
Okay.
Yeah.
Yeah.
So sometimes sometimes you can only break apart the plus connection.
Right.
And I think you know, some of the speakers we've got some speakers here that are both ways. Some will you've got bus bars for both the plus and minus terminals, and some just have the bus bars on the plus terminals. So the other curve that's interesting to look at is THD versus level. And you'll find that typical power amplifier comes up and rises up to the point where we get to 1% THD. Okay. Now, some will be more gradual, some will be rather abrupt. What's different about the AHB2 is it does that and then abruptly clips.
Mm-hmm.
Just like your preamplifier would do, just like any of your line level components would do. They're clean and then they clip. Okay. Now, why is that desirable? One of the things that's desirable is that we've got this much of an advantage.
Yeah.
In terms of THD, and I've got a chart up here at 1% THD. If I've got a 100-watt amplifier, 1% is 40 dB below the music, but it's only 20 dB below 1 watt.
Right.
Because 100 watts is 20 dB watts. It's 20 dB above 1 watt. So 1% distortion, minus 20 dB watts. If I've got speakers that are 90 dB SPL at 1 watt, 90 minus 20, 70, that means that the distortion in the room would be 70 dB SPL. That's like having an air compressor running in your room. Now, it's harmonically related to the music. And music, to some extent, maybe to a large extent, masks it, but we're relying on the music to mask the distortion of the amplifier. So let's, go down further here, go down to 0.1% distortion. Now we're 40 dB below 1 watt, 60 dB below 1 watt when we get to 0.01% distortion. 0.001 distortion, we're 80 dB below 1 watt. So now with my 90 dB speakers, the at 100 watts, when I'm putting out full power out of my out of the amplifier, that means that the THD would be 20 decibels above my threshold of hearing. Still loud enough that I'd be concerned about it. And if you go to 0.001%, which is where the benchmark AHB2 power amplifier is, we're 120 decibels below the music, and we're 100 decibels below 1 watt. And so what that means is that the distortion produced by the AHB2 power amplifier is always going to be below 0 dB SPL. So we're not relying on the music to mask the distortion of the amplifier. You know, we shouldn't have to use our music to mask the deficiencies in our electronics. We can build electronics that are good enough that we don't have to do that.
Yeah, and you're basically getting very consistent distortion at any power level by doing this approach.
The other thing that I didn't mention, that I should mention, is this curve right here is the 8 ohm curve. And if we take a conventional amplifier and go to 4 ohms, we end up with a curve that's higher. And if we go to 2 ohms, if the amplifier can do 2 ohms, it gets even higher. And if you take the AHB2, and I'll draw this in a different color here so we can see it, the 4 ohm curve is virtually right on top of the 8 ohm curve, and the 2 ohm curve is barely above the 4 ohm curve and well below what you get with most power amplifiers.
Gotcha.
So it's the ability to drive low impedances without having an increase in distortion, and a large part of that is the feed-forward error correction.
Yeah, because there are some amplifiers that they don't do well under low impedances, and that's a big problem, especially at high power levels.
Mm-hmm. Big problem with a lot of Class Ds, and a lot of Class Ds have quite an increase in distortion as you go up to higher power and as you go up to higher frequencies. So high frequencies and high power both end up being difficult situations for a lot of power amplifiers.
People think that the low frequencies tend to be harder to drive, but in reality, some of these amplifiers, if they run out of feedback, you know, at higher frequencies, and you're dealing with low impedance lows especially, that's where the amp misbehaves the worst.
And actually what it is it's the harmonics of the low frequencies.
Yeah, because there's not a lot of music content at high frequencies.
Right.
Exactly.
But if I've got low frequencies with a lot of harmonic content, or just plain harmonic distortion from the low frequencies, this you know, this inability to take that out is, you know, if we're talking about frequency again, the inability to reduce the high frequency distortion is something that's a challenge for anybody that's designing a power amplifier. Especially challenging if you're designing Class Ds. It's just an order of magnitude more difficult when you're designing a Class D.
And we have a block diagram here of the feed-forward error correction. Maybe you want to go over this.
Yeah, so on the left, you see the input signal, and that goes into the main amplifier. We're showing that as a 100-watt Class AB amplifier. There's a feedback loop. There's actually a filter in that feedback loop. There's a low-pass filter to prevent the amplifier from oscillating. A feedback loop can cause an amplifier to oscillate if you don't roll off the feedback at high frequencies. So the feedback is actually rolled off at a lower frequency on the AHB2 than you might roll it off in a conventional design, because we're intentionally allowing the feed-forward error correction to take over at high frequencies. So you see the output. There's a sinusoidal output plus a distortion component. That is compared to the input with the 1 watt amplifier down at the bottom there. And that happens to be a Class A amplifier. Doesn't have to be a Class A, but it happens to be in our implementation. And what you get coming out of that is just the distortion signal. You can see that it's inverted from the waveform at the top, and those are actual waveforms captured from the distortion component of a Class AB amplifier.
So now let me ask you this: if the main amplifier is 100 watts and then the feed-forward error correction amp is only 1 watt, what happens when you exceed the 1 watt? Does it become less effective?
Great question. But take you back to this chart that I put on the screen in the beginning here.
Yeah, let me get back to that. Hold on a second.
All right.
I'm stuck on the wrong screen.
That's all right. But let's look at 1% distortion. Let's suppose your main amplifier was creating 1% distortion. What is that? That's with a 100 watt amplifier at 1% distortion. My distortion is minus 20 dB watts. Okay, so that means that to do the correction, I don't need 1 watt to do the correction. I need 0.01 watt to do the correction. So
Okay,
my 1 watt amplifier is way more than sufficient to do all of the correction that needs to be done on the 100 watt amplifier.
Gotcha.
And there's a picture of the AHB2, the benchmark DAC3, and the benchmark LA4 line amplifier, which is a line level preamplifier.
Yep. Cool deal, John. Appreciate you explaining that. I don't think we've ever had a full explanation of how this THX circuit works. So
yeah, it's very clever. You know, we really appreciate the collaboration with THX. It's unique to this particular power amplifier. There is no other power amplifier with the THX that uses the THX patents. There have been other power amplifiers in the past that have used feed-forward error correction, but it's a very unusual approach, but very effective.
So someone's saying 100 watts seems like a little limited, but your amp is much more powerful than that, especially when it's bridged. Why don't you give us the power numbers on it?
Yeah, so when you bridge it, you basically get 4 times the power into an 8 ohm speaker. We're at like 380, 390 into 8 ohms when you bridge it. And to bridge it, there's a little switch on the back. You flip the switch, and now you're in bridge mono. So and there's speak-on connectors on the back of the amplifier. You move the speak-on to the mono output.
And it's interesting because a lot of amplifiers, when you bridge them, you only get maybe twice the amount of power because they're really current limited.
Right.
You're getting close to theoretical. Theoretical bridging should give you 4 times the power.
Right.
Because you're getting twice.
So we're very close to that that 4 times the power, and this is what's also very important is that this 4 ohm line is right on top of the 8 ohm line. Okay. Mm-hmm. When you go to bridge mono, your 8 ohm speakers are going to look like 4 ohm speakers.
Yeah.
To the power amplifier.
And
if that line was higher, you'd lose a lot of the advantages of the AHB2. So,
and I've seen that where I've bridged amplifiers that have bridge feature, the distortion goes way up.
Almost always. And so it's always been a rule of thumb that when you run bridge mono, you're going to have higher distortion. Well, guess what? When you do that with the AHB2, you don't. And
what kind of power do you get when you bridge it with a 4 ohm load?
So I think it's 510, 518 518
And it's
bridge mono
stable?
into
It's stable
yeah.
for 4
Oh
ohm
yes.
bridging?
Yeah.
Yeah, good.
And part of that is because of the feed forward error correction. Feed forward error correction is inherently stable. So if I put a capacitive load on there, it doesn't go into oscillation. So we can drive capacitive loads, we can drive inductive loads, we can drive, you know, the flat panel electrostats and so forth without a risk of going into oscillation.
Right.
And so that's a big
Someone
difference.
says your amp is 259 watts into 2 ohms, both channels driven. So that's very stable. Is that what it is? About 260 watts at 2 ohms?
Yeah.
Yeah, that's good. Question here is, can it handle 2 ohm dips? We just kind of answered that with that power rating. Yeah.
Yeah.
So yes, the amp is stable to 2 ohms.
Not only can it handle them, but the darn thing stays clean.
It doesn't get distorted.
So it doesn't get distorted. It doesn't do this like a conventional amplifier would do. It stays clean. In this room here, I've got we can't see them right now because they're back behind the screen, but I've got some line arrays in here that are 2.4 ohms, and we run those with the AHB2. Run them right up to full output. No problem. The thing never gets warm. So no problem driving 2.4 ohms, but more than just no problem, stays clean.
Linear and clean. Yep.
Yeah. And you know, the other thing that's interesting is, you know, if you look at crossover distortion, that as you start driving difficult loads, you start driving capacitive loads or inductive loads, and speakers are you know, a mixture of inductance and capacitance, and these zero crossings. This crossover distortion happens at 0 volts when you're running a resistive load, but when you're running a reactive load, these crossings actually happen at different places, because it's the reversal of current that causes this distortion. It's not the 0 voltage crossing.
Oh, okay. Interesting.
Your push-pull devices in your output stage actually cross over when the current reverses, not when you cross 0 volts. And so this crossover, these crossover distortion points actually move all over the place depending on the instantaneous load.
Cool deal. Well, John, I appreciate you dropping the knowledge, and we have a bunch of videos from Benchmark Media Systems on technical topics, not just on these products, but just on various things about DACs, distortion, noise floor, all that stuff. So I put this all in a playlist. I definitely recommend you guys check it out. Do you have anything else you wanted to drop here, John, before we go? Are you going to be at Expona next week?
We are going to be at Expona. I'm personally not going to be at Expona, but
you're demoing? You have a demo room?
We've got 2 demo rooms going, and it's going to be a great show. And who knows, I might even pop in, but always a possibility.
Well, cool, guys. If you're going to Expona next week, please check out Benchmark Media Systems. What's your location?
We're with Studio Electric, and we're also with I'm sorry, I should have had that for you. We'll put that in the comments.
Yeah, for sure.
And give you an update on that. Yeah, we're with Chesky Audio also.
Oh, good people.
Some really exciting speakers that David Chesky's son.
Yeah, I saw them at Florida Audio Expo.
They are phenomenal. We're very excited about teaming up with him, and so we'll be showing with him in one of the rooms, and then with Studio Electric in another room. Studio Electric always has a wonderful sounding room, it's always great teaming up with them.
What a cool thing. Dave is he's like 17 years old. He built the speakers basically in his garage, you know, and he started his own company, and it's all sound engineering. He's got a
Yeah.
single driver with 2 passive radiators, so it's got twice the cone area, so it's properly done in the box. It's got the right Q, and the tweeter's really close to the woofer, and he's got a whole, I think it's like an HDF cabinet. It's a really rigid cabinet, and they're small, and they're like $500 a pair. So
And it's a 3D printed cabinet.
Yeah,
And so there's actually really clever acoustic design going on inside the box, and just a lot of good engineering went into it. He's a sharp guy.
Sure. Well, John, appreciate it again, guys. If you like this video, please hit thumb up, hit subscribe, check out the links below for Benchmark Media Systems. You guys have really cool white papers, so there's a lot of knowledge there, and then also all the product pages are there as well. And don't forget about our Patreon channel at patreon.com/audioholics. We appreciate your support. And until next time, my friends, keep listening.